Hi everyone, welcome back to the Qiskit live seminar series. I'm Maria Violaris and I'm your host for today's seminar. I work part-time with the Qiskit community team alongside my PhD in theoretical quantum information science at the University of Oxford. I'm delighted to be joined today by Professor Elham Kashefi, who will talk about her research on how we can check that noisy quantum computers are actually giving us the right answers. So before we properly start the seminar, we'll wait a few minutes for everyone to arrive. But in the meantime, I'd love to know where you're all joining us from. So please let me know in the comments in the live YouTube chat, which you should find on the video, and let us know where you're joining from. I think some people have started already. We have people joining from Chicago in the US and Raleigh, North Carolina, Montpellier in France, Chicago again, Portland, Oregon, Israel, Ottawa in Canada, Belgium and Brussels. Great. Lots of different places. I'm joining you today from Oxford, where it's getting towards the later part of the day. Yeah, great to have you all joining us from all these different places. And Costa Rica as well. Great. So, yeah, before we start the seminar, I'll give a brief introduction to our speaker. So today we are joined by Professor Elham Kashefi, who is the Professor of Computer Science at the University of Edinburgh and is the CNRS Director of Research at the Sorbonne University. She has pioneered research in various aspects of quantum computing, including by co-founding the fields of secure quantum cloud computing and practical verification of quantum computing. She also co-founded the quantum cybersecurity startup VeriCloud, which is based in France. And recently, Elham was elected as the chief scientist for the UK National Quantum Computing Centre, the NQCC. And she leads the NQCC Quantum Software Lab at the University of Edinburgh. So that's a very large amount of different organizations. And we also have a fun fact that my current PhD supervisor here at Oxford, Professor Vladke Vedral, was also Elham's PhD supervisor a while ago. It was one of his first students. So it's a small world in the quantum information community where we found this this connection. Cool. So we can start in a couple of minutes. Thanks, Elham, for making the time to join us today. I'm sure you have a very busy schedule with all these different responsibilities. And for everyone joining us online, I encourage you to use the live chat throughout the seminar to ask questions as they come up, and then I will keep an eye on the chat and hand over your questions to Elham during the seminar, and we'll also have some time for questions at the end. So make sure that you keep us updated in the chat about what questions you have.
Awesome. Let me first start. Thank you, Maria, for the nice introduction. As we just discovered, we are quantum sisters, so this is even more exciting to be here. But thank you very much also to the Qiskit community to invite me. Super happy to present. Shall I go ahead? We're good to go?
Yeah, we're good to go. So yeah, please go ahead.
Excellent. Wonderful. So as Maria encouraged, please do ask questions during the talk. I will also pose to make sure that if there is any question before moving forward. The general topic that I have in mind is to talk about verification of quantum computing, a little bit about recent results as well as about the field. Well, let's just dive into it. So what is the main question regarding verification of quantum computing? So we have this quantum drama, as I would like to say. We are going to have more and more powerful quantum devices that they are emerging. And at the same time, we as the verifier are very limited with our computational power. It must be the case that we as a classical verifier should not have the same power. But why I'm calling it a drama in the sense that we don't really know that do we really obtaining quantum advantage? Did this thing did something beyond our classical capacity? Is it really implementing something correctly? Is it really a quantum correct simulation, or is it just a bunch of noise? Of course, you can immediately think that for some problem like factoring, I don't care if it's quantum or not quantum. You can just ask the answer and multiply and say, yeah, good, I got the factor and I know if it's working. But that's not a verification. Just verifying that this whatever machine it is able to implement, for example, factoring. But we're talking about real quantum computation and devices. And as I go along this is not only just a scientific discussion, but it's actually trying to help. My dream is to actually help with building quantum computer influenced by theoretical work that we can do. So that's the deal. That's about quantum verification. And indeed, you might have heard this word, in so many different contexts, and everybody from scientific all the way to the industry, we want to have efficient, practical, robust, secure, hardware agnostic, standardized certification. So that would be very useful, something that exists already for example, high performance computing, exascale computing on classical devices. And what we have in so many different review exists, and we have written one recently with few colleagues, that is essentially we have zoo of different type of protocol, and you can forever compare them and characterize them according to the assumption they make about the underlying devices, assumption about the noise model, and then on characterizing depending on their samples and about complexity, about efficiency. So it's so many things, and I didn't even put everything. We see randomized benchmarking, tomography, Hamiltonian learning, all the way to error mitigation, whatever. So we are not there. We don't have one solution fits all. And my talk is about to offer yet another route to explore this landscape. So in particular, what I will be talking and want to present in more details is this recent work that I have done with my colleague, Harold Olivier from India, and two of my students, Dominique and Luca, which now has already graduated as in Kwandela. But what we have been focusing is really looking at the verification, as I will define in details, for the computation that can be implemented on quantum computer, or more precisely, the bounded quantum polynomial algorithm, and answering it for the current NISQI devices, and answering the question of overhead. And as I want to convince you at the end, so we managed to take this verification protocol, which on their own, they're slightly different with benchmarking protocol or mitigation protocol or self-testing protocol or tomography protocol or shadow tomography protocol. They are in the same zoo, but we are arguing that now they are very efficient in terms of number of sample that is required, as well as they are the weakest in terms of assumption that they make. So that's for me to show you where verification sits. And depending on how much time we have and how far we go with the question, etc., is like this is actually is not just one protocol, is a framework that we have developed that now, using this framework, we're trying to come up with a new method for error mitigation, new method for quantum capacity measure, like quantum volume, etc., a new method for even doing multi-party computing. So I might say a few things on that model as well. So where the story started, the story of the verification, the question of verification started even as a complexity question. So I think Daniel Gottesman and then Umesh Vazirani posed this as a complexity question, and even Scott promoted it with the $25 challenge back in 2007. When we asked this question, does it the case that any language, any algorithm, any problem that you can solve using a quantum polynomial computer, i.e. if I give you a quantum computer that can run it, can I find an interactive protocol, which I'm going to define in a second and more precisely, where the honest prover, if it's really have a quantum computer and is it really able to run quantum computer, be able to convince a verifier like us, which is having only classical computer, that yes, I'm able to run it. So this is a mathematical definition. Does BQP admit an interactive protocol for where the honest prover is itself is in BQP and the verifier is in BPP? But it's exactly formulation of, can I use classical computer, an efficient polynomial time classical computer, to decide whether quantum computer giving me the right answer or not? I know it seems a very simple question, but it actually, you would think that, if the fact that we believe quantum computer cannot be simulated with classical computer should actually pose that, can we actually know that we cannot even simulate it, even certify that the answer is correct if we are not trusting the devices? So that was the question when it was raised. And more precisely is exactly, you have a quantum computer that you can connect, you ask a question, but you're not trusting, not trusting. It could be that, you're either in the crypto or complexity scenario, or you're not trusting because you don't know inside this black box how noisy it is or how actually quantum it is. So we have a computational limited verifier. This is the terminology I use, verifier client. We have a powerful quantum server that we make no assumption on the way that this device works. And we want to certify the correctness of the computation, okay? And this question was posed, and over the years, we have so many different way of answer, to this question. And these answers are the following form. So yes, indeed, we can certify correctness of computation and BQP if the verifier is not completely classical. So still the question is 100% correct, open, if you wish. If we can answer it, if the verifier can prepare some random qubit. This is the work that myself with Anne Brodman and Joe Fitzsimon proposed back in 2009. At the same time, also there was other colleague, Haranov, Benor, Eman. We also put another solution for the interactive protocol, which you give a little bit of quantumness. And Vlatko back then actually wrote a popular article about this work. It's a very nice one. You give a bit of quantumness to the verifier to be able to bootstrap to actually verify the big quantumness. So that was the original idea. And then there was another breakthrough, very nice result by Reichard, Unger, and Vazirani, that they also consider different scenario, that imagine you have now two quantum computers, that they are entangled, but non-communicating. Is really like sort of a Bell inequality test. And you can use a purely classical verifier that is certifying whether these two quantum computers are working or not. But the condition, again, you see, is not pure classical verifier certification of quantum computer, because now you're asking two quantum computers which are entangled, but they are not classically communicating, which is more or less the same as quantum communication. And then there came amazing recent result by Urmila Mahdav from Berkeley and then now in Caltech, that he said, okay, now let's change the game and make some assumption. Instead of going for information theoretical verification, we go assuming there are some problems that they are even hard for quantum computer to solve. And these are the learning with error, LWE, the post-quantum security type of protocol. Using that assumption, assuming quantum computer cannot break it, she come up with a protocol actually that is pure classical verifier, is able to certify the correct functioning of the quantum. So each one of these protocols have its own pro and cons, and depending on the scenario, we can argue and we can go how they compare. But what I would want to say that these are all falling within some general family that I like to present to you to get the general idea, and then we can revisit that why we still had some work to do and hence the new results. So, but this is the status regarding answering that $25 question of Scott Aronson. And meanwhile, there was not just 3 results. There has been many, many other protocols. We wrote another review, which is probably now out of the, is not anymore update even. But again, many protocols were designed regarding several approver. How can we reduce the number of rounds? How can we reduce communication? Do they provide blindness, privacy or not? The number of observable, beautiful set of theory. And either they go using the self-testing route, either they go through non-locality game, either they go to some sort of crypto technique. But the status, what I want to impose by observing this figure, that it's been really much a very complexity-driven field, a very beautiful theoretical field that has been trying to answer this question in general, that what is the minimum quantumness that we need to have? And there's plenty of open question there. But let me, before moving forward, to give you a flavor of what this interactive proof system is, because it's not the same as error mitigation approach, is not the same as randomized benchmarking approach, is not the same as other, if you wish, the hardware-driven approach. It's more kind of computer science-driven approach. So what is verification as an interactive proof system? Interactive proof system is a framework that has been used a lot in computer science for defining complexity classes in PNP and all the polynomial hierarchy. And in this context, what we are asking is that, can we have a protocol that you have the verifier, which is us, we are trusted, we know what we're doing, we have our devices, and we have some randomness, and then we have interacting with this black box quantum computer, which we call it prover, or it could be a device, or it could be a server, it could be in the cloud, as you wish. And after this interaction, so I'm asking question, the answer comes, and again, I'm asking another question, the answer comes. We are creating a joint density operator, this B of nu, that it depends on the randomness of verifier and depends on the strategy and the noise and deviation of the devices, okay? And now we want to be able to prove a property of the following form, that at the end, when we did our interaction, there will be two scenarios. There is a flag that will be announced accept or reject. So it might be the protocol reject, i.e. nothing has happened, or the protocol accept. So now the property that we want for this protocol to have is the correctness, in the sense that if there was no interference, if there was no noise, if everything is going ahead, if the quantum mechanic is correct, which we assume is correct, and if the device is really following the instruction that we are believing is defined by quantum mechanics and follow the step of protocol, then the protocol should accept, should not reject. So this is the correctness of the protocol. And also the answer should be exactly the correct answer that we are expecting. So that's the correctness property of interactive proof system. And the soundness probably is also very important, as the correctness is that now the whole point of this protocol is to detect, like an error detection mechanism, that if the device is so noisy, if the prover is lying, if there is no quantum computer there is any sorts of deviation has happened in this interaction, then the verifier should reject. So we don't want to have been in the scenario that we have accepted the outcome, but in fact we have the wrong outcome. So we want to reject an incorrect output, except probability that has at most exponential small insecurity parameter. So we cannot have a perfect correctness and perfect soundness, and that's another very interesting question on its own, that in all this IP, because of the little bit freedom of, you can be, any lying device might also get lucky and to produce whatever result we want to have. So those are the mathematical property of this interactive proof system, correctness and soundness, and a little bit more precise in order just for you to appreciate the generality of the scheme is that, so we have a subspace that we are trying to guarantee that after our protocol, we are not going to end up in that subspace. The incorrect subspace is the subspace that the flag is creating this projection state of the acceptance, and yet the outcome of my quantum computer is totally orthogonal. So we want to write the statement, and I show as English sentences to a mathematical, that no matter if you look at the formula below, that if you sum up, no matter what is the strategy of the server and device in deviation, and no matter which randomness the prover, the verifier has used, the probability that I ended up to be in this bad subspace, I'm projected in this bad subspace, is bounded. So that's exactly mathematical property of the verification. That's the definition of verification. And if you wish, is the strongest notion of verification. We can pause in a second to make sure everybody's with me, in the sense that it's not I'm just guaranteeing about the fidelity of the outcome, or I'm just saying the device has working, or I'm just saying that, oh, if it's IID, I'm saying I make no assumption whatsoever. This big omega could be any deviation, Markovian, non-Markovian, entangling, classical simulation, whatever you want to put. No matter what deviation of that server device, I would be able to bound the scenario that the outcome is correct and I somehow been fooled and accepted the outcome. So that's why what we are saying, this is a very strong definition of verification. Obviously, if you have been verified, that means the process of your quantum has been close enough to the exact channel that you wanted, the outcome has the highest fidelity, the noise has been below some threshold, but mathematically that's the definition. This is a good moment if anybody have a question before we proceed about the definition. You can shoot me, Maria, otherwise I'll continue. So far, so good. Okay, so that's the definition we wanted. And as I said, this is a definition that is common among all those papers that I refer. And then what is so big deal? Here you should start kind of getting worried that, how on earth, I don't even tell you what is the CPTP map that is the deviation of my noise. I didn't say that if it's time dependent or is not time dependent. How on earth I can bound effect of a general noise model without having any assumption on it. And that's the magic of the cryptographic toolkit that we have been all using, that in general, this is familiar even in the case of key distribution, that you have a very general noise model, which is entangling and is acting on your entire quantum system together with the private system of the attacker, or you can think it a very general noise model you have. But if you're carefully design the toolkit from cryptography, or if you want even a bit fancier, less fancier, what is it, some enough randomization, it allows you to reduce this general, coherent noise to something very simple that is testable, and that's the subspace, test subspace. This is the reduction. In a sense, we don't make any assumption on the noise, whether it's IID or etc., because the crypto hiding will reduce this massive task of verification to a very simple error detection. That's the underlying picture, that how impossibility of something that I cannot even classically simulate, but I'm able to very efficiently tell whether it's correct or not, is because of this reduction. So really, just before moving on, it's just like, okay, you write your general formula. So what is the proof technique? You write your quantum computation that you want to write. You're assuming this P is the exact computation. You don't need to really follow the calculation. But what I want to show you, that then there is this omega, this beast that I didn't make an assumption. And yet through my proof, I'm able to reduce it and give an upper bound, because there is a magic. The magic is that I have inserted enough randomization in encoding of my computation, so that omega will be reduced to a bunch of very simple off-diagonal, the diagonal Pauli matrices. So if you look at our proof technique, is that I put omega, but at the end, I just need to look at the overlap of just simple single Pauli on my error test. So I'm essentially ignoring what's happening to my computation, and I just look at what is my test subspace. And that's happening because of crypto. And why I'm telling you this, because some of you might come from a different field, and we all know that this Pauli tooling, or if you have seen it like a T design that is used for the randomized benchmarking, or in the all sorts of various toolkit that exists for the quantum advantage testing, we always keep coming back to this wonderful theorem that if you have a quantum state and you have randomized it enough, i.e. either using one design, which is here in the Pauli tooling, or two design, which is a Clifford tooling, then you can get rid of any off-diagonal noise parameter and reduce it to only diagonal, which make it manageable. So that's it. That's the toolkit. We have done it. We have squeezed it over the last decade. We are understanding it. We are optimizing it. And then you're asking the question is, okay, so I say that I have formulated this as a complexity question, but it seems it's powerful enough to use it as a benchmarking tool, as a certification tool, as a, really testing whether my quantum computer is working in a practical setting. Because what we really want to do in a verification is that we want to prove that these devices that we are building and we soon reaching to the 100 qubit, 400 qubit, 1000 qubit is functioning correctly. And we want to make minimum assumption about the resources, and as well as using the minimum resources in terms of not bringing the whole overhead of fault tolerance. Can I say something about my 1000 qubit machine that is working? The point is, to some extent, the framework is the right framework, but we revisited everything and realized so far we have been so concerned, and we have done all these protocols perfectly practical and nice and wonderful from the verifier point of view. But what we have come up so far in the field is a nightmare for server and device, because we were a little bit like theoreticians. We said, well, this is a problem of IBM. They building quantum computer, they better be passing all of our tests. So the reason that maybe we have not yet seen that the verification become run out of the mill in all of the existing platform to be run is because we have not been focusing to make this protocol also very efficient and useful from the device point of view, because we were thinking very cryptography. Okay, the devices are nasty. This is the quantum computer. They better pass our test. So we are trying to see how much of the framework can be revisited and optimized so that it's not just practical for verifier, but it's actually practical from server point of view. And why do I mean by practical? Means the current protocol are oversensitive. So I mean that even if you have a device which is NISQI, in the sense that it's really quantum computer, it's making all the effort, but it just happened to be noisy, we would all the time reject. So we will definitely make sure that we are not accepting wrong outcome, but we never accept any outcome to begin with. And to some extent, qubit overhead was there. Of course, we are optimizing them and saying a linear overhead, but linear overhead is still overhead. Asking a device that is 100 qubit and suddenly give me 10,000 qubit to do verification is also still overhead that we want to get rid of it. And it was also, in a sense, too ignorant of hardware. I know we want to do hardware agnostic verification, but we should be able, if we want for the short term in the next 10, 20, 30 years, help the roadmap of really implementing quantum computing in a verifiable way, to understand a little bit about hardware. So that's the beginning of this new era that I want to talk about. It was a long introduction of trying to tell you what we're trying to do, but it's essentially going back to revisit this protocol and just to showing where was the bottleneck when we look at it. So there's lots of protocol, there's lots of way that people have tried to optimize. Indeed, we are proudly saying that we have only linear in the size of your general computation. So it means if your computation, your algorithm is require 100 qubit, a linear factor of 9 linear server overhead was the protocol, and that's not too bad yet. But usually all of this protocol, when you do it in this technique that I was showing, which I didn't show you, but like sort of a reduction of the crypto bringing to error detection, it gives you a polynomial soundness, meaning that you have only polynomial confidence, polynomial in the size of your computation. For example, the protocol that for showing proof technique, if you put just one trap, it gives you very, very low confidence about that. Did I really get the correctness? I.e., translating it gives you a fidelity which is not very, very close to 1. So it gives you some confidence, but not close to what you want. And then suddenly in most of this protocol, we need to bring bootstrapping via fault tolerance encoding. So in the scenario of quantum input, quantum output verification, we have a bottleneck that if you really wanted to give high confidence exponential, and by the way, this is the case for any protocol, even in randomized benchmarking, error mitigation, the reality is that we can give a very bounded confidence in what we're trying to do, unless we bring lots of assumption or we just bring back the whole fault tolerance. So this is the real huge server overhead, and this is kind of scratching your head that, well, should I wait to have a magical fault tolerant quantum computer, or can I do something in between? So that's what we set for ourselves as a challenge. And the new result that I advertised earlier is that, okay, we said that what if We don't go for quantum input, quantum output, which is the most general setting, and is a very important setting because it's still a lot of quantum sampling problem that we have, a lot of quantum chemistry problem. If you wish, they are a little bit like a quantum output problem. I can comment on that later on. But we said that what if we just limit ourselves to a large class of interesting problem, classical input and classical output, that's our good beloved BQP algorithms, and then try to revisit and say that, can we remove that bottleneck? And it turned out to be very, very easy. This is the wonderful thing is when you have the new PhD student comes and challenge you about what you thought is correct, and they just actually reprove you. So we have this new protocol, which was the revisiting of everything that we have done a decade ago. It is now really have no overhead. If you give me 20 qubit, I work with 20 qubit. And it turned out, if you want to have only classical input and classical output, you don't need to do full fault tolerance for bootstrapping. You only need to have classical repetition code. That's obviously make a huge difference. So instead of asking for a big number of qubit as the overhead, I'm just asking more and more of repetition. So you give me 100 qubit, I repeat that. So we're going to go to look at it. So that's the reason that now I'm redrawing that diagram and saying verification is in a sweet spot for the BQP, classical input, classical output. It's the protocol that allow you to have the weakest assumption, no assumption about your device or noise, etc. And it's really minimum few sample. It give you exponential correctness on the honest but noisy devices, and also give you exponential verification on arbitrary deviation. So let's go and try to go through all of this protocol. I want to start now running exactly like how does the protocol looks like, and it's like this. And you might not be impressed, but we are very impressed because it's the first time we managed to write a protocol in one slide. Usually our protocol, it takes few slides, so you never even read it. But now this is it. You know, if you're a practitioner and want to go and implement this on Qiskit, you know, that's all you need to read. You know, okay, there's lots of things that it goes into it, but fits into the one page. So let me try to show how the protocol works with an example rather than showing you the full picture. Any questions so far? Do we understand the task at hand before I continue and present the example?
Yeah, please let us know in the comments if anyone has a question.
Okay, so far everything is so clear. Everybody knows what verification is about. Excellent. So imagine now, after all of my advertisement, you have such a computation and you want to show that how do I get this highest level of verification implemented on my platform. So the first thing, everything that you say, you can also write it in a different model, but the most suitable way of describing the idea is if you're thinking your circuit is implemented in this thing, is in this a slight format, as if you can see it. So my target computation still is a quantum circuit, but I have rewrite it in such a way that all my global 2-qubit entangling gate is done at the beginning. I have particular input, but maybe I have added some ancilla qubit in the state plus. Then I have this single qubit measurement layer, and they are mid-circuit measurement and some adaptive circuit gate based on that. And now, first of all, just a note that we wrote a paper ages ago, measurement calculus, that any normal quantum circuit computation can be written in this form. So it's not like a particular picture. And it's, for some of you are familiar, this is in fact measurement-based quantum computing or one-way quantum computing or cluster state computing. That's also another alternative way of doing computation. The most important thing is that for our protocol to be implemented, if you want to go at the level of the hardware, so it's really, really important to have these classically controlled gates. So in a sense, I don't know how to run our verification if you're not providing mid-circuit measurement. And mid-circuit measurement are something that people anyway are implementing as part of the building block and milestone for the fault tolerance. So we're not asking something that is impossible, but currently for some architecture, you might not have it. So this classically controlled gate is one element we need. Okay, so this is my normal circuit picture that maybe some of you are familiar, and now I'm going to rewrite it in a bit of a graphical picture. So instead of drawing those wire and then saying those gate is happening, now I said that, like, imagine my quantum computation that I want to run is this particular 5-qubit computation, which is essentially a graph that those edges are my 2-qubit gate, and on each qubit I have prepared the state plus, and then on each one of them I do some measurement in the XY plane with alpha 1, alpha 2, alpha 3, etc., and off we go. So first of all, this is a universal model, so you can write any algorithm like that. And now I need to do a little bit of massaging in order to do my verification. And what we do is called blind target computation. Instead of implementing our computation as it is, we are actually randomizing it. Again, thinking about randomized benchmarking, error mitigation, circuit characterization, tomography, this is not a surprising. Usually when you want to do benchmark, you take your computation, you make a many random version of that computation. So the randomization is in this picture is that instead of I prepare all the qubit in plus and then go ahead and do my 2-qubit gate and computation, I randomize in among the 8 parameters. So these are the random state preparing the XY plane. So plus theta is 0, plus e to the I theta 1. So now I have a family of computation. They are all implemented on the same underlying architecture and the same underlying connectivity, same processes, same algorithm, some measurement to be performed, some measurement based on measurement, some etc. to go. And that's a new requirement when I go and talk about the implementation. So I say that, for our architecture, we want mid-circuit measurement, not a big deal, but we also want the ability, and that's very, very important key. That's how we are stepping out of usual certification model. We are assuming that the input state can be prepared in a hidden fashion. Remember, I talked about verifier and prover, interactive protocol, a randomness of the verifier. That's where the notion of us and the device will come. So me, as a verifier, as a tester, should be able to randomize and prepare my input on my quantum computer in a hidden way, in a random way, and then making sure, and in another interpretation of this noise, this preparation noise is independent of the rest of my computation, and off you go. Then the whole machinery go through. So we have this hidden input preparation, which we call the blind target computation, and we have this framework of the computation based on mid-circuit, and then all the element is there. Now we can implement verification. So what do I do for verification? Sorry?
Is this kind of random input preparation something that's normally people are able to do on hardware anyway, or is it a kind of additional thing that people building hardware need to think about to use this?
It's a very good question, and if you allow me, I come back to it in a second. So let's say that I need to have that, and I'm not telling you yet how to do it, but there is a mechanism to implement it, and that's an extra requirement. And I have plenty of things to say. So please ask that question to me, that how do I provide the condition of this hidden input preparation? Because that's so far it has been exactly like a normal computation, but this hidden input preparation is an important key step. But let's say that we have implemented that somehow. So now what is the notion of insertion of trap, or if you see this here, I said a test and compute protocol. So now I'm going to do running bunch of computation and bunch of tests, and the way that they are defined in this way. So my target computation, this gray graph and qubit implementation, etc., is exactly as it is probably a probabilistic computation. I have no clue what is the answer. Okay, the 5-qubit, I know what is the answer, but this could be my 1000 quantum chemistry simulation that I have no clue what are the right answer. The whole point of it, that this target computation, I cannot classically simulate it, and I have no idea of what is the noise model and what has gone wrong. So I have lots of those gray computation, which is, you could even imagine that is tailor-made for the hardware. But the trick, the tiny little trick that I'm adding, is that I take the same graph, the same underlying architecture, the same 2-qubit gate, the same gates that is used for the other one, and I create the test run of that computation. And what does it mean? So depending on the graph that is dictated by your algorithm, so this is tuned to your algorithm, you're creating a k-coloring of this graph, where the most important thing is that all the qubits which are not red are prepared in 0, 1, and all the other qubits are prepared in the random state. And because these 2-qubit gates that we are applying it over the edge are control Z, When you apply the same gate, if it was target computation, they might get entangled and you can create a complicated computation. But when you're running it on the test run, when you're applying control Z, which one qubit is 0, 1, one qubit plus theta is not entangling them. So they are a bunch of isolated qubits. So I am running the same computation with the same underlying connectivity, but the test run are a bunch of isolated qubits. And they are designed in this way because suddenly, for those red qubits, I deterministically know what should be the answer. I prepare them in plus theta, and I'm going to measure them in the same basis, so they are not deterministic. It might sound a bit weird, but what is really happening is that I'm running all this computation in parallel, as I'll show you in a second, and then suddenly the same run of computation, sometimes they are probabilistic. I have no clue what's going on. There is no answer. There is noisy. Sometimes they are deterministic. They are useless computation. They're a bunch of 0, 1, but they are exactly deterministic computation that only the verifier knows the answer. These are the test scenario, and they are actually classically simulatable. So the reason now, so so you might ask, why am I doing it this way? Why I take that computation? Why I'm creating a test similar to that? The point is, now usually if you look at all the other protocol for noise characterization, at this moment they need to make an assumption, well, the noise is really exactly the same whether I'm doing my test over the Clifford computation or whether I'm doing the test on other scenario. Oops, sorry, my mistake. So the framework of adding the crypto, adding those input preparation, and every theory that I'm not telling you at all about it, it guarantees a very, very key property. It guarantees that because I use the crypto framework, the server, the device, the noise cannot distinguish, am I in the target scenario, am I in the test scenario? So I enforce this indistinguishability. It's not like I assume it and I believe it, because physics is like that, and because my device, I have done tomography on 10 qubit, and surely my 1000 qubit going to have the same there. I make no assumption. In dynamically, whenever I'm running computation, I lose my word. I get excited about this point. I enforce the fact that the device is as if it's the malicious adversary. The device cannot say that, okay, now I'm doing a computation, so I'm going to well behave and actually I'm going to do all the random thing and produce a wrong answer. But the moment is a test qubit, I have known that this is a test, so I'm going to behave well. So if you think it in this sort of adversarial model, you can see that we are treating the nature to be adversarial. We don't know when the nature is going to be noisy, when it's not. So we're making sure that the nature cannot distinguish. So that initial randomness and that crypto framework allow me to say that the noise in both scenarios are the same, is indistinguishable, and now it's done. So because now instead of running 1000 overhead, etc., that we were asking before, we just say, okay, you give me a 5 qubit computer, I'm just going to work with 5 qubit computer, but I'm going to run 1000 times the same 5 qubit computation. And talking to experimentalists, asking them 1000 qubit versus asking them 100 times running it the same 5 qubit computation is a huge difference. But interesting enough, it works for our purpose, because now we randomize, we have n number of rounds. T of them are randomly chosen to be test. D of them are chosen to be the computation, and we mash them around. And then what happened to the verifier? Back to the good old verifier. The verifier can look at all those test runs, and you see the test runs are different because they are different coloring. The green qubit, I have no clue, they are random. But the red qubits are my little test qubit that I know deterministically what should be the outcome for them, and I will check them if there is enough threshold, which now this threshold is tunable depending on which noise or which confidence or which fidelity you want to afford. They pass the threshold. I know, I'm guaranteeing by the theory that the gray qubit is good. So I never did any testing on the gray qubit, but because they are randomized, our theory allow you to give a confidence regarding the gray computation based on the correctness of the outcome. And that's very typical witness detection for the model. So that's the test and compute. It took me a long time to explain, but hopefully with this little example, it become more clear. So protocol has lots of other feature. You can do redo option. These are the new feature that didn't exist in the previous work, and they all were, we pursue them because this was the thing that in the experimental adaptation they were required. The redo option is that when you're trying to create this sort of random input or several round, it's very likely that your device might be unintentionally failing. So you want to have redo option while it doesn't affect the security property. We wanted to have this very strong notion of composable security amplification, because entangled noise, or if you want time-dependent rounds, can be detected with exponential, and they are not the same as a classical one. So we had to go to this much more higher level of security, which is called composable security. Everything is fine-tunable in the sense that depending on the noise of your device, that most of the time platform knows where they're coming from, and depending on what is your underlying architecture, how many qubits you have, you can always play around what should be the number of runs, what should be the test. So now we are able to talk in a language with our experimentalists to make sure we do their best for the server while we are still testing the server. And it's scalable in a very precise way that if I have a 100 qubit machine, I will work with all the 100 qubit for doing the computation and several other runs of the same 100 qubit to do the test. So I'm not cutting my computation for some part to be tested. So these are all the good features that in the implementation are very useful. I noticed that I want to still reach to it sometime. So maybe if you're interested, reach out to me. I can send the slides. So there is the new, I'm not doing justice to all my students who actually did this proof that because to do this new protocol, which I demonstrating a feature, we needed to go to this abstract crypto security framework to provide us. So it's not coming for free. The fact that we have all these wonderful properties just because in fact we have to provide the security in this higher level of model that then allow us to prove, yes, indeed, there is this tunable parameter, and indeed we are able to detect any deviation of the platform as a malicious deviation and detected it and provide information theoretical verification rather than computational. And much more important, something that is like, unless you read the paper, you're not appreciating, is that we are able also to tune it in the sense that if the device is noisy, but we know that to which level of the noise is the good noise. Like, I'm happy to have up to 80% fidelity of my gate. So you can tune the number of run and threshold of acceptance to be 80%. It's not like as soon as a trap test said wrong, we are going to reject, which was the previous methodology. Now we are able to accommodate a threshold of the noise while still giving a certification of the correctness. So in short, do we need to wait for fault-tolerant device to achieve provable advantage? The answer is no. We are now decoupled the requirement for the verifiability and fault tolerance, and we are able to use any qubit that this NISQI device are providing for the computation, as well as able to provide this exponential security. But of course, very importantly, you still need to have high-quality qubit. Even if you whatever we do on theory, if your devices are so noisy, there is no magic. We should reject because those computations are low fidelity. So it's still, we're reaching somewhere in between, but the importance is still that maybe some sort of partial fault tolerance would be enough, or maybe better quality of the computation response. So it's still, there is plenty of room to improve. And now I want to come back before I finish up the question that you asked, Maria, regarding hardware adaptation. So as I say, classically controlled gate is the same thing as mid-circuit measurement, which is more and more popular, and more hardware platforms are trying to provide it. Is a challenge, but is clear. But you will ask, what about hidden input preparation? This is something that we are requiring it for our protocol, but maybe it's not in the milestone of every hardware platform to provide it. Because indeed, the best way to implement this hidden input preparation is that if you have a photonic link, in a sense, you want to provide to a verifier ability of creating a random single photon in its own lab and then insert it to the device, or from the device, get a random photon constant to do receive and measure, or create this entangled non-communicating. So we look at it, and the solution, the best solution to implement precisely in the hardware level is the architecture of photon matter entanglement. And surprise, surprise, this quantum photon entanglement is also precisely what the many company and many architecture are pursuing for scalability. Because we know that after we put 1,000 qubit in one fridge, the only way to continue is to do the interconnection and photon interconnection. So again, we are waiting very opportunistically for people to implement that, and that's precisely what we want. Obviously, even in the superconducting, there are results that are coming using microwave or different platform, even photon platform, people have showing it. Trapped ion is definitely a promising in order to have this optical link. NV platform, photonic already have it. And I'm very happy that you asked this question, because even last week we put a paper out that my dream comes true, and we actually demonstrated it not just for photonic, because we implemented protocol with the group of Philip Walter a few years back in Vienna. The photonic was the most trivial way to do both quantum computation and quantum communication. But we never had an architecture of photon matter. So in the David Lucas group and the work that was done by my collaborator, Peter Dromotos, so that they really take our protocol, they really implemented it, and the idea is, okay, you have a server, which is the ion trap quantum computation with the memory qubit, with the long fidelity that we know, but they also have this architecture. Those photon can be, those ion trap qubit can be entangled to a photonic qubit that can be linked using a fiber optics to a remote verifier. So we precisely had the element of that. There is a memory qubit, and there is maybe next slide showing it better. So yeah, so this 2-qubit ion trap platform that exists in the Oxford team has two types of species. And so one is very good for the memory, one is very good for networking. The networking qubit can emit a photon when you shine a laser on it, and that becomes exactly the photon that goes, in the, I think in this experiment, maybe it was 300 meters away, using an optical fiber to an isolated place that we call it a client or verifier, which the verifier is just trying to make a single qubit measurement to produce the randomization of the qubit that is sitting inside the entangled server. So the purple qubit of the server entangled to the photonic qubit of the client make a measurement. As a result, is randomly preparing the purple qubit, and now the game starts. So every purple qubit that is randomized, then you can do a swap in order to swap it with the memory qubit. Now, in the next iteration, the memory qubit randomized, and I can take again the network qubit to re-randomizing it and exactly implement the step of our protocol. So here is the first demonstration of the implementation of the protocol with the ion trap and photonic, and that's the building block. Of course, we have done it with 3 photon, if you want, 3 qubit, but now we believe this is the model that we can replicate with the NV platform, with the other platform, hopefully, as well as superconducting. And just quickly before wrapping up, to advertise a few other upcoming results. As I said, this is really a framework. I cover it with showing you one simple example, but there is a beautiful theory underlying it that allows us to, in fact, make a big link between error detection and verification. This is a methodology that many people are trying to pursue, that error detection might be the only thing we need for time being, just to know that the computation is correct for time being without doing any correction. So we are doing error detection, and we are exactly know how to turn any error detection to a verification protocol, or making any verification error detection. And that gives a huge new, if you like, framework of exploiting different way to make protocol even more optimized. The other thing that is coming is that already even the protocol that I represented has some limitation, because I said I'm running 1,000 run, and we know very well with the current devices, some days are the good days, some days are a bad day. So you very much have the noise dependent framework. And it's very good that to know that which set of round of the protocol were good enough to keep, and which are the one that we should post select. So we have a new paper coming out, which is using verification technique. We do error mitigation in the sense that we know how to post select and pick up the good round that is still fit to our framework of verification, but the abnormal run that, like, I don't know, laser was broken down can be thrown away. So there is this verification based error mitigation comes. There is also another work of the people are coming to keep you interested to check us is the benchmarking. That also something along the line of quantum volume, but in a much stronger hardware agnostic, that we verify the complexity classes a device can run it. It's not just about the particular depth or width, but we actually can give a certification of all the set of function and the capacity of a device. And that's what we are very excited to be complementing using this. There is this recent algorithmic oriented benchmarking, and now we want to have verification oriented benchmarking coming out. And we can do multi-party computation if you have several clients, my favorite topic that is linked with the quantum cloud. So if you have now several clients that want to run a computation on remote server and provide the privacy, again, using this new verification technique, we have a recent work that is coming out to show you. And just to pitch as a final remark, so what I really believe, and again, back to the question you were asking, Maria, so it is very much our framework thinking about distributed architecture, the ideal architecture that enable us to talk about verification, and all the machinery that I explained is this, distributed architecture interconnect. So our message is that indeed the requirement from hardware people is to make sure that they have interconnection there. But when they have interconnection, by design, they have this very strong notion of verification that can, on top of it, you can have the privacy, scalability, error mitigation, multi-party, capacity test, everything for free. So that's it. I'm going to stop in here. Thank you very much, but I'm happy to answer any question that people might have had.
Great. Thanks for the talk. That was really good, really nicely explained. And yeah, I remember seeing the paper you mentioned near the end about the experimental implementation. That was good to actually understand what was shown in that result now, which is really nice. Yeah, I was going to ask if it's been experimentally implemented. That's really cool. Yeah, so please let us know in the chat if you have a question. We have one already about the framework used for the verification, if it exists as a quantum language in itself, or if it's a collection that sits on top of existing quantum languages. So yeah, I think it's kind of about the framework used for the verification.
Okay, I assume here by quantum language, you mean quantum programming language. We're not talking about the decision problem. So yes, it's for time being, as I say, it was a very theoretical protocol. There's all of this protocol that is not just us and others are implementing is not integrated in any programming language, but this is our deal. So we are already in our team at the Quantum Software Lab. We are launching a very open source framework using the Quest. So Quest is a programming language that is an open source simulator developed by the Oxford team. And we are trying to lead a library that is implementing our verification protocol, especially that there's so many other things we want to implement on top of it. But it's not, so in short answer, it's not integrated in any programming language, but it's a pseudocode. So you can integrate it in whatever favorite language that you want to have. And we believe this should actually goes in the much lower layer. It's a little bit like a calibration or quantum control that we usually don't see when we run some high-level program. All those compilation and calibration has been done on the lower level. And here I should advertise in the project that several partners in UK, we are leading as Innovate UK project led by River Lane. We are hoping to integrate this type of verification at the lower level at the operating system. So indeed, you don't even need to do something. The verification is done at the compilation part, but we are not there yet.
Cool. Yeah, that sounds really interesting. Thanks. So yeah, I also had a question. At some point earlier, you mentioned part of the protocol which depends on which algorithm you're running. Could you explain again?
Yes. So so the picture may be in here. So when I put this algorithm in here, so I'm saying that in a sense, what's the best way to say? So if I have very limited connectivity of architecture, I have a very specific quantum algorithm that I want to run. Before, we would take this algorithm and we would embed in a sort of a large graph and large error correcting code, etc., if you want to run. But now we have, it's just a matter of theoretical. Now we understand, okay, if this is the circuit you're doing, and as a result, when you write it in this framework that we're saying, it's become that particular graph, well, that's it. We are not going to now ask you to change your connectivity or change your native gate or rewrite your algorithm in a different way. We're just taking the underlying connectivity of your algorithm and we build the test on top of that. So instead of tailor-making the algorithm for our verification protocol, we are tailor-making the verification protocol for the algorithm that you want to get the guarantee on top. So it's a bit of a workflow that has been changing.
Mm-hmm. Cool. Yeah, that's nice. Yeah, just another question is, yeah, so in this experiment where the protocol was implemented with the ion trap, could you explain again how the random preparation was done in this example?
So, so the model is, instead of prepare and send, is receive and measure. So we know that is, think of QKD, they are very much equivalent. If I want to create a random qubit on your system, either I prepare it randomly and send it via a photon link to you, so then you holding a qubit that is randomized by me, or the other way around is that we make an entangled qubit. So I make you and me to have a bell pair entanglement. And then when I measure my qubit randomly, because of the entanglement, your qubit has been randomized. And you don't know exactly what the state is randomized, but I know exactly because it depends on my measurement outcome. So the model of the protocol is precisely like that. So we're taking the 2 qubit that is always sitting in the ion trap, the purple qubit that you're seeing. So by shining a laser on that network qubit, a network ion trap qubit, it's emit. Now I'm going to pretend I know something about the experiment. It emits a photon, which that photon qubit is entangled with the with the network qubit of the server. So here, this blue laser, if you wish, that's another third qubit, which is entangled to the purple qubit. And that third qubit is the one that I'm sending in the fiber optic to the client. Now the client is capturing it using the detector, and now that qubit of the client is entangled to the purple qubit, and I'm now measuring that qubit. By measuring, and if you look at the photon, you see that this blue photon in the side. So when you're measuring the photon in some random basis θ1, which is only known to you because you put your modulator. You know, we have the modulator on the client side, which is not known to the server. So we make a measurement, and this A1 outcome is the secret knowledge that the verifier, the client, has in order to know what is the random state that sits in the server qubit. So from server point of view, is like a randomized totally mixed state, but which we actually experimentally verifying that if we throw away all the information of the A1, M1, and A3 that the client is gathering, the state of the server is totally mixed state. Whereas knowing that information, you're able to create that randomization. And then what will happen is that here you will see I'm just accessing to randomizing one single qubit rather than the entire system. But I can swap it. So I create the network qubit to be random, then I'm swapping the state. So I'm swapping this random qubit to my memory qubit. So in the second square, you see that the memory qubit now is randomized. So hence I can reiterate again the procedure. Again, I'm shining a laser in the network qubit coming out, I'm measuring it. So in each iteration, I'm randomizing one qubit, and then I'm pushing this randomization using swap gates in the server side.
Cool. Nice. Well, I think that's all our questions. So we can, yeah, bring things to a close. Thanks everyone for joining, and yeah, I hope you all learned some interesting things about verifying the results of quantum computations. So yeah, this maybe just before we wrap up, there's been one more question that I can.
Sure, happy to answer.
Are you able to take as input for the verification protocol target quantum algorithms written in many quantum computing languages?
It's a bit like similar to the previous question. So the answer is yes, because in fact, it's nothing to do with our protocol in the sense that you write whatever algorithm that you've written, and at some level of compilation, this will come to, let's say, that to some quantum circuit instruction. And then we plugging our pseudocode for that low level. If you like, we are doing verification at this very low level. So yes, give me whatever high-level programming language you have. We go through the compilation to translate it to a bunch of instruction of what are the quantum gate you want to run. And then we translated that quantum gate to be a verification computation. So the answer is yes, but some compilation need to be done. But that's not a limitation in the protocol, and there's no limitation. Somebody need to do it. So please do it, whoever asked this question. I'm happy to help. But yes, it's actually a very good way of doing it if you can start receiving different code, and they are all translated at the low level instruction that need to be done.
Cool, thanks. Yeah, so thanks everyone for listening. We're going to have another seminar next week, again at the same time, 12 p.m. Eastern time. And for that one, we'll be hosting Professor Sean Carroll, who will talk about quantum mechanics and space-time. So it should be a fun talk. And yeah, just before we close, Elham, do you have any final comments for the viewers about anything you want to let them know about?
Yes, if you like verification, we have postdoc position, research assistant position, intern position. So just drop me a line, because we are trying to exactly along the line of what we discussed to expand implementing this protocol on various hardware, implementing them on various platforms. And we just launched our quantum software lab in collaboration with NQCC. And top of our agenda is to do the verification. So we need hopefully interested collaborator to come and join our team. So we have several positions open. Please drop me a line if you're interested.
Great, thanks for letting us know about that. I hope, yeah, maybe some of our viewers are interested in that opportunities there. Cool, so thanks everyone for joining. Thanks again, Elham, for the great talk.
Thanks very much for having me, Maria. It was fun. Thanks a lot.
Great, thanks. And we'll see you all next time. Bye.
Bye.